In this video, we are going to talk about multiplicative inverses. As a quick refresher, I want you to answer this question. So pause the video and tell me what is in the set Z mod 7Z star. Okay, so pause the video and tell me the elements of that set. Okay, well, this set, remember that star means a group of units, and so that means the values in this set that have a multiplicative inverse. And so really this should be the numbers. So 1 is its own multiplicative inverse, 2, 3, 4, 5, and 6 are all going to be in here. So if you notice, there's 6 things in there that happens to be 1 less than 7. Well, and just to figure out, maybe we want to figure out what the multiplicative inverses are. We can kind of see this play out in this table. So again, this is a multiplication table, so I take multiplication of these two things, mod 7, and I'm left with whatever appears in this table. So zeros are kind of boring in here, and so I'm going to fill in this row, and then I want you to fill in the rest of the table and resume the video when you have. So I paused the video and I completed the table here, and so we can see that whenever we have a product of 1, that is going to indicate to us that we have a multiplicative inverse. Okay, and let's just see here. Let's see, and there's one more right here. Okay, so the way that we see this is that 1 would be its own multiplicative inverse. 3 times 5. Those are multiplicative inverses here, and so they are in this group of units, and then 4 and 2 are, and then 6 its own multiplicative inverse. So again, the group is 1, 2, 3, 4, 5, and 6, and so the size of this group is 6. Okay, and so now again, I'm just making this connection here that the group of units, its size is 6, and our modulus was 7, which was prime. So then maybe I want you to make a conjecture. What if you look at the group of units for Z mod PZ, where P is prime, what's the group of units there, and then what is the size? Okay, so pause the video, take a shot. Okay, well, maybe this is what I'm thinking. We could have the set consist of, well, actually 0 is not going to be in there, but 1, 2, 3 up to P minus 1 is going to be in is going to be in here, and so when we count that up, there's going to be P minus 1 things in the group of units. Maybe. Let's see. Okay. Next proposition. Okay. It says for P prime, every non-zero element has a multiplicative inverse. Oh, well, I guess my conjecture was right. So 0 was not in this group of units, right? Yep. And then, so that would mean the size of the group of units is P minus 1. Okay. And then, so just another way of saying this is that for A and B, we can find, when we're looking at Z mod PZ, we can find two numbers that are congruent to 1 mod P. And more specifically, B is A inverse. But now the question is, how do we find that? And well, that ends up being a little bit easier than we might suspect. So certainly you can make a table like this. Otherwise, there happens to be a nice algorithm that we already know that can help us find this inverse. Okay, so if we want to find 17 inverse mod 29, all we have to do is the Euclidean algorithm. So pause the video, try to work the Euclidean algorithm out. You are going to see that the GCD is 1. Surprise, surprise. Okay, and then once you work out the Euclidean algorithm, pause or resume the video, and we will look at the next step. Alright, so I completed the Euclidean algorithm. Here we go. We did show the GCD is 1. Surprise, surprise. Now, remember that our previous or in the proposition, which we didn't prove, and it's actually kind of a quick proof extending from one of the other theorems we know. It said that AB must be congruent to 1 mod P. Okay, so this is equivalent to saying that we can find a number such that if we look at, or we find a number B such that AB plus PV, for instance, is equal to 1. Okay, so this looks a lot like the Euclidean algorithm if we know that the GCD is 1. And we've shown it's 1. Okay, so now to find this B and this V, which we don't really need that, all we have to do is the extended Euclidean algorithm. So that is to say we want to start with our second to last line here. Okay, so and then we isolate the 1, so 1 is equal to 5 minus 2 times 2. Okay, and now I repeatedly substitute in. So here I would actually solve for 2. 2 is equal to 12 minus 2 times 5, and I'm going to just write these all out here. So I'm going to isolate the remainder. 5 is equal to 17 minus 1 times 12. Okay, and then 12 is equal to 29 minus 1 times 17. Okay, so now I want to return to my statement here and continually resubstitute. So I'm going to substitute in the 2, and we've done this before, so I want you to pause the video and work this through and resume the video once you have this all worked out. So I completed the extended Euclidean algorithm, and I got this at the very bottom. And so remember, I was looking for that number B that was multiplied to A with the modulus and this other number. So I don't care about, oops, and I actually miswrote. This should not be 12, that should be 29. But then you can see the modulus is here and my original number was here, so then that means that 12 is actually the multiplicative inverse of 17. So I'm just going to make a little note here to answer the question at last. 17 inverse mod 29 is congruent to 12 mod 29. Okay, and so then that completes the problem. So again, just to find the inverse for a particular modulus that happens to be prime, I can do the Euclidean algorithm, extended Euclidean algorithm, and then when extended, it should just be the coefficient of the number that we're interested in, and not with the modulus. So that's kind of the end of this video, and then in the last video we'll talk about fields and what those are, because we've been kind of dancing around this idea, and we'll formalize it at last.